Hello everybody. In this video I'm going to be going over this problem. So we have a 1 by 8 rectangle and we have these 6 purple or pink segments and they are basically zigzagging from one side of the rectangle to another. And so you start up here at this top left vertex of the rectangle and you zigzag 6 times until you get to the top right. What we want to find is the minimum value of the sum of these 6 segments, or the sum of the lengths of these 6 segments. So let's consider an easier problem where we just have sort of 2 zigzags. So if I draw a rectangle like this, and I want to know, I draw something like this, I want to know the shortest length that the sum of these 2 segments can have. So I could draw, like over here, and I could draw over here. And sort of our instinct is to say like, well, maybe it's the middle. The middle might have the shortest, but how do we actually prove this? Well, there's 2 ways we can think about this, right? And the first way is a sort of common, well, not common, but it's very useful for considering sort of the shortest length. If you're considering the shortest length, and that is to think, what would light do? Because so you take your problem, which is purely mathematical in posing, but you turn it into a physical problem. Say, what would light do? Because light always travels the fastest route that it could. So if it were trying to zigzag from here to here, let's say now we're taking a light beam, so I'll do a yellow color. Hopefully that shows up. But light, we know if it were to, hit a mirror or something and then bounce back, right? We know a property of light is that the angle it makes, it makes congruent angles before and after bouncing off, basically. So these equal angles of reflection. And so we can, and that's sort of the answer to our problem is that if we made these 2 angles congruent, then we would have our shortest length. And we would have sort of, similar triangles and stuff, and we could solve the problem. But maybe this is a little more complicated because we have 6 zigzags. So I don't think thinking about what light would do would really solve this problem because we could we could solve the problem for just this rectangle alone, but this rectangle could vary depending on the first 2 zigzags. So we need a more versatile approach to this problem. Well, what what about the angles being equal that like really makes it the shortest length? Well, consider we know how to find the shortest length between 2 points in space, right? In Euclidean space. It's just a straight segment. But what's hard about it in this problem is that we don't have just a straight segment. But what if we made it a straight segment? In other words, what if I were to take this rectangle and reflect it over its side. So something like that maybe. Um, Let me see if I can make this a little bit better. That's rough. Anyway, but if we take this rectangle and reflect it over, so these sides are supposed to look equal, then we know if I were to continue this ray, what I know about this angle is that this angle is equal to this angle. And so if this angle is equal to this angle, which is equal to this angle, then what we know is that this would be a straight line from here to here. So let me see. Let me try drawing something a little better. So in other words, so now I have a much better reflection. So if I just consider, right, this, um, this path here, right, this is obviously the shortest way to get from, we'll call this point A, and I'll call this point C. But we want to know the shortest path from A to B using our reflection. Well, what we can do is reflect this segment over the side here, which gives us this angle equality because we knew these were equal because they were vertical angles. So if I reflect this triangle, then I get this. And so this solves the problem for one zigzag, or I guess two segments. But we still have this problem of 6, right? We still need a way to complete this, right? But it sort of looks like the same approach would work. If I were to reflect, say, like right here, like, like that, right? We see that if we just keep sort of reflecting, we'll get a long chain of things that will eventually go down to another point. And if we're trying to minimize the length from this point to a point down here, well, let's figure out what that would end up being. Is that if we have 6 segments, right? Notice how when we had 2 segments, we reflected once. So this length was twice the length of the original. Then if we have 6 sides, we're reflecting 5 times. So this is 6 times the original length. The original length is 1, so this is the length of 6, and this is a length of 8. So then we have all these zigzaggy segments. Say like that. I know that's kind of rough, but obviously each one would have a height of 1. So these are occupying equal, they should be occupying equal spaces, but they're not. Then what we're looking for is simply this, right? If all the zigzags lined up perfectly, then we could make a straight line segment, and that would be the minimum length. And so we just have to find the hypotenuse of a right triangle because it's a rectangle that's been reflected, so it keeps its right angles of 6 and 8. So the answer is just 10. Thank you for watching, and I'll see you in my other videos.